This is our second lesson on vectors. We're filling out our guided notes with all the technical terms and notations. So first of all, writing down the definition of a vector. And a definition of a vector is a quantity that has both magnitude and direction, but it is a quantity. It just has two aspects to it, okay? The geometrical representation for it is we use a directed line segment, also known as an arrow, and in the picture that we see here, we've got vector P, and vector P does go from point P to point Q. So the arrow goes starting at point P and then it goes towards point Q. P is called the initial point. Q is called the terminal point. Sometimes these are referred to as the tail and the tip. The tail being where it starts, and the tip being the tip of the arrow, what it points towards. So we're going to use an arrow symbol, and actually the symbol we're going to use doesn't look like a full-on arrow. It actually is what I call a half arrow. So when we put this symbol over the letter or the symbols, if it was vector P or vector PQ, this half arrow symbol is what we draw above it. Okay? And this is what you see here, this little half arrow above. We could say the vector PQ. We could say the vector P. In the textbook or anytime it's typed, they typically write it with a big bold letter, but handwriting don't do that. Okay. We're going to talk about magnitude. We've talked about magnitude in the first lesson, but to formalize it here, we're using the distance formula. And this is the formal distance formula when you're going from point 1 to point 2. And so we have x1, and then there's x2, but you start with the ending and subtract the beginning. Typically, I just say, well, let's just call that the change in x and the change in y. So we square the change in x, we square the change in y, add them together, and take their square root. That will be the magnitude. So we're going to do these two problems here. First of all, the magnitude. I see that my vector, the a, the change in x is from 8 to 7, to negative 7, which is 15. It's actually negative 15, but you're going to square it, so it doesn't matter whether I write 15 or negative 15. The change in the y from negative 1 negative 4 to negative 2 is positive 2, and so we square that, add those together, and we get the square root of 229. I do want exact answers when we can, but eventually we are going to write decimal answers, and we'll use 2 decimal place approximation. For number 2, we have the magnitude of the vector rs, and so we see the change in our x is 8, the change in our y is 4, square those, add them together, take the square root, and we get 4 root 5. Standard position is what we many times will refer to with a vector, and the standard position is specifically when the initial point is the origin. Component form is when we look at a vector, we say the change in x, comma, the change in y. I know we use the letters a and b, but it does mean the change in the x direction and the change in the y direction. When it is in standard position, that if the terminal point is ab, then the vector components, meaning the change in x, change in y, is also ab. So to find the magnitude, we write it this way, the square root of a squared plus b squared. To find the angle, because remember there's magnitude and direction, we use the arctan of b divided by a. We have to note the quadrant that it's in, because remember the arctangent on our calculator only uses quadrants 1 and 4, and in quadrant 4 it's going to give a negative. The direction is in the positive, so we always give a positive answer for the direction angle. So if it was in quadrant 4, your calculator is going to say something like negative 15 degrees, but we have to realize that that means that it would be 360 minus 15 degrees, and that would be the angle. So we're going to use our calculator for these because we are going to be finding decimal approximations. First thing we need to find is our magnitude. We do note that we're in quadrant 1. So when we do arctan for the direction, it will be exactly what the calculator says. Well, I mean the approximate that the calculator says. So the magnitude is 25, and for our theta, we get 73.74. For problem number 2, we note that we're in quadrant 3. The calculator will not give us an angle in quadrant 3. So we're going to have to take the angle that we get from the calculator and realize that it's going to be 180 degrees plus that. So the magnitude of this vector n, is root 10, which is approximately 3.16. And then we put our theta, we do arctan of 1/3. And then we add 180, so we get 198.43. So when we're going to write a vector, we just subtract our x's and subtract our y's. But it's very important that order matters. You have to decide which one are we subtracting from. We always do the ending point minus the starting point. When I do it, I just look at these arrows and say to go from the starting point 3 for the x direction to the ending 6, we would have added 3, so that would be the change in my x. To go from 5 in the y direction to 3, we would have subtracted 2, and so we have 3 comma negative 2. This next one, I look at the change in my x, the change in my y. We've got -7, -9. Here we're going to do the component form. We're finding the magnitude and the direction of the vector. So for the components, we know to go from 2 to 4, we'd add 2. To go from -9 to 1, we would add 10. And so we have our component form here. To find the magnitude, we square those and add them together. Take the square root and simplify to root 26, but we want the decimal. So it says 10.198 or something, so it rounds to 10.20 rounding to 2 decimal places. And the direction angle, we do arctan of b over a. We note that this is quadrant 1, so exactly what the calculator states, and that's 78.69. We have that. For the next problem, we're going to use the graph and look at what is my change in my x and the change in my y from the initial to the terminal. And we see that we changed 5 in the x direction and to -3 in the y direction. So that is our component form. The magnitude is to square both of those, add them together. We get square root of 34, which is approximately 5.83. For the direction angle, we note that we are in quadrant 4. Now you look here and say, oh, it's in quadrant 1. No, if we put it in standard position, it would be in quadrant 4. We're pointing into quadrant 4, and that's whenever we're finding the direction angle, that's what we're thinking about. So arctan of -3/5, we're going to get a negative angle in our calculator, and we're going to add 360 to find that it's approximately 329.04. When we multiply, we can't multiply vectors, but what we can do is we can multiply a single vector times a scalar. So here we can see this is like 1v, this is the length of 2v. Same direction, it's just twice as long, meaning the magnitude will be twice as long. Half of v would be half as long, or the magnitude would be half as long. But again, it points to the same direction, so all of these vectors are parallel. This one here is negative v, meaning the opposite. So what was our terminal is now our initial point, and it's pointing to the other one, which used to be our initial, but now it is the terminal point. So multiplying changes the magnitude. Adding vectors, well, when we add u plus v, we get what is called the resultant vector. So this one really is saying there were 2 vectors that got us from the very beginning to the final end. But we could have done that as one vector that is the combination, meaning the addition of vector v plus vector w. So we get a resultant vector. Subtracting is no different than adding. we just add the opposite vector, and that's what this is telling us, that here we had vector v, and then at this terminal for v, we did the opposite of w, and that gets us to the final resting place. It has a resultant vector also, but just when you're thinking about subtracting, you're adding the opposite vector. So these are the operations that we have. When we multiply the vector, we are multiplying each of the components. We can write it this way, and this is the way I prefer to write it. A lot of times it looks nice and clean that way. V plus W, we just add our A's and we add our B's. For subtraction, now this looks like subtraction, but remember what we're doing is adding the opposite of vector W. A unit vector, kind of like a unit circle, is a vector that has a magnitude of 1. So just like a unit circle has a radius that is 1, a unit vector has a magnitude that is 1. We reserve the letter U whenever we're talking about a unit vector. So the only time we're going to use this symbol U with vector is when the vector has a magnitude of 1. And if we want to find the accompanying unit vector, meaning I have a vector that's long, but I want to find out what would be the components if it was only 1 unit long. Well, what we do is we take the vector components, whatever they were, A, B, and we divide both A and we divide B by the magnitude of V. So whenever you take the vector and divide it by its magnitude, we will get a vector in the same direction but has a magnitude of 1. So let's do an example. Here's vector V. Vector V has a magnitude. It is not 1. It happens to be the square root of 17. And that's how long vector V is. But I want the components for a vector that has a magnitude of just 1, a unit vector. So I take the components, -4, -1, and I divide them by each by square root of 17. Now I need to reconcile, rationalize my denominators. Don't want square root of 17, and I end up with -4 root 17 over 17 and negative root 17 over 17. Standard unit vectors would be a vector that's 1 unit long that starts from the origin, but more specifically, it's either on the x-axis or on the y-axis, meaning a 0-degree vector of 1 unit length, or a 90-degree vector with 1 unit length. To get those, the ending points at standard position, you would have 1, 0 for a unit vector that's on the x-axis, and we would have, whoops, just a minute. There we go, I fixed that. And if we went in the y direction, the terminal point would be 0, 1, and so the vector is 0, 1. We use the letter I for the vector on the x-axis and J for the vector on the y-axis. This is the 90-degree vector, and this would be the 0-degree vector when we talk about their direction. We can see a little sketch of it here. This would be vector I, and this here would be vector J. So let's look at how we write linear combinations using I and j of any vector. We've got the components 2 and 5, which says we're going 2 units in the x direction and 5 units in the y direction. Remember, I and j mean that. I means x direction, j means y direction, and so we can just write this as 2i plus 5j. 2i plus 5j. And for number 2, we've got -7, 3, so we write that as -7i plus 3j. So it's saying -7 in the x direction and 3 in the y direction, the I vector and the j vector. For number 3, we need to find the components, and the components are 4 and -14, and so it's 4i minus 14j. And the same thing with number 4 is we need to find the components, and we just look at how we change, and we end up with the components 8 and -1. So it's 8i minus j, and that's like saying minus 1j. I just don't need to write the number 1. Trigonometric form. This is going to be very, very similar to when we were doing polar. So to talk about a trigonometric form when the vector is 1 unit long, then that means we're pointing to where the arrow is coming from the center, from the origin, and points right to something on the unit circle. And because it's on the, if it's a unit vector and it's on the circle, then the components would be cosine theta, sine theta for the x and the y. If we want to write it as a linear combination, we say cosine theta I and sine theta j. Just like we would do AI plus bj, it's cosine theta I plus sine theta I. When it's not a unit vector, because a unit vector is just plain and simple because it's right there on the unit circle, we can just use sine and cosine. When it's not on the unit circle, meaning the magnitude is more than 1, then what we do is we say, oh, it's going to be magnitude times the unit vector. Okay? And the unit vector is cosine theta, sine theta, so it's the magnitude times cos theta, sine theta. I can distribute that magnitude, and so sometimes we write it this way. I think it's cleaner to just write magnitude times cosine theta, sine theta. If we were going to go so far as to write it with i's and j's, which we rarely do, we write this whole thing. Magnitude times cosine I plus magnitude sine theta j. When we get to applications, or when you do applications with vectors, this is a little bit more common. We are not going to do much with applications. We're doing just a very basic introduction to vectors. So here is a vector in its unit vector format. And what we want to do is write it in trigonometric form. So the first thing we notice is the components are -2 and 2, so we need to find the magnitude. We square each of those and take the square root, 2 root 2. We need to find the angle, noting that we are in quadrant 2. Since this is negative and then positive, that's in quadrant 2. When we plug this into our calculator, we're going to get a negative in the calculator. That's meaning it's an angle in quadrant 4. And so what we have to do is we have to add 180 degrees to whatever the calculator says, and then we'll be in quadrant 2. So that's 135. So now, to write it in trigonometric form, we just write it as magnitude times cosine 135, sine 135. That's it. Here's another problem. We don't have the components. That's not written in the linear format there. So we need to find our components, and we find that's 2, -6. We find the magnitude. We find the angle, noting we're in quadrant 3. So again, we're going to get in quadrant 3. The calculator, we plug this in, the calculator is going to give us an answer in quadrant 1. We're going to need to add 180 degrees to get to quadrant 3. And now we write it in trigonometric form. We have magnitude times cosine of that angle, sine of that angle. And that's the end of our guided notes.